Welcome to Lecture 16, whose topic is static equilibrium. In a sense, this lecture is easier than the preceding ones because we're dealing with the special case where objects are neither accelerating in the linear fashion, nor undergoing angular acceleration, nor even rotating. So it's a simpler situation. It's the situation architects need to worry about when they design buildings that aren't going to fall over or bridges that will stand up. Let's look at some pictures of systems in static equilibrium. Here we have the world's tallest building, the Burj Khalifa, with a height of nearly 3,000 feet or a little over 800 meters, remarkably tall structure. Here we have the Almelo Bridge in Spain, gorgeous structure. It looks like it should be toppling over to the right, but it isn't. Why isn't it? Because it's engineered to be in static equilibrium. Here we have the Balanced Rock in Colorado that looks precarious, but it is in static equilibrium. It's neither rotating nor accelerating. We have a stork standing on one foot, and we have a ballerina standing on one foot. These are all examples of systems in static equilibrium. What's required for a system to be in static equilibrium? Well, first of all, it can't have any net force on it, because if it had a net force on it, it would be accelerating, and it certainly couldn't be at rest. Couldn't be in uniform motion either, but in particular, it couldn't be at rest, which is what it needs to be for static equilibrium. But that's not enough, because it might have zero net force on it and not be accelerating, but it might still have a torque on it, and therefore it might be rotating, or its rotational motion might be changing as a result of that torque. So the conditions for static equilibrium are that there be zero net force on a system and zero net torque on the system. So in one sense, this is an easier problem to deal with because in F equals ma, or torque equals rotational inertia times alpha, the A and the alpha, the acceleration and the angular acceleration, are both zero. But because we have to worry about both torques and forces, problems involving static equilibrium can get quite complicated. Now, there's a problem when we start talking about zero torque on a system. And the problem is that torque is defined relative to some pivot point. The example I gave in Lecture 15 was to pull on a big wrench and try to tighten a bolt. And then I gave you this picture that suggests that the torque depends not only on the force you apply, but on how far it is from the pivot point. Now, when an object is actually going to undergo changes in its rotational motion state as a result of a torque, it's pretty obvious what to use as the pivot point. It's the point about which it's going to try to rotate. But the problem with static equilibrium is we don't have any rotation, so we don't have an obvious choice of pivot. And it better be the case that there is no torque about any possible pivot point, because if there was one point about which there was torque, even if there were lots of other points about which there was no torque, we would get rotation about the point at which there was torque. Now, I don't have time to prove this. I would normally do so in an hour-long physics class, but I'm not going to take the time. The problem, again, is torque depends on the location of the pivot. It's obvious if an object is rotating, but in equilibrium, it's got to be zero about every point. Here's what I'm not going to have time to prove, but is a useful theorem. As long as the net force on the object is zero, another condition for static equilibrium, and the torque about any point is zero, it's pretty straightforward to prove then the torque about every point is also zero. So what seems to be a problem with torque, that we have trouble identifying the pivot point when the torque needs to be zero about every point, is not really a problem. If we can prove that the torque is zero about any point we choose, and we're welcome to choose our point at our convenience, then the torque will be zero about every other point. And again, that's true only as long as there's no net force on the object, but that has to be true also if the object is to be in static equilibrium. Now, one of the common forces that's acting on objects at our surface, of course, is gravity. How do we deal with the torque due to gravity? Well, let me give you a couple of examples here. Here are two pictures, one of the Tower of Pisa, a rather surprising structure because we expect it to topple over to the right, but if it is in static equilibrium, it's not toppling over to the right. It has zero net force on it and zero net torque on it. How is that possible? The reason the Tower of Pisa looks improbable is because we know instinctively that there is a torque due to gravity on the Tower of Pisa. We have to think about where that torque acts. And it turns out that every object has a point called the center of gravity, and it's as if all the mass of that object were located at the center of gravity, at least for the purposes of the torque that gravity exerts on the object. It turns out, and I'm going to prove this in just a moment, that when gravity is uniform, the center of gravity corresponds with the center of mass. But those two things they mean something different. The center of gravity is the place where gravity acts like it's acting for purposes of torque, and the center of mass is the point at which the mass seems to be concentrated for the purposes of Newton's second law, and when gravity is uniform, then it turns out those two things coincide. When the only torque is due to gravity, so there are no other torques acting on the system, then the center of gravity must lie directly above the pivot. If it was a little bit off center, there would be a torque. Let's look at it in the context of these two pictures. So there is the gravitational torque, the gravitational force acting on the center of gravity of the Tower of Pisa, which is its center of mass, which is roughly in the middle of that cylindrical shaped structure. If there were just that force acting, then there would be a torque associated with that would cause the tower to topple over to the right. But there's another force, and it's the force of the ground acting up on the tower. And two things happen. The force of the ground balances the force of gravity, so there's no net force on the Tower of Pisa. It's not accelerating up or down. Furthermore, because those two forces are acting at different points, they result in torques that are in opposite directions. The torque due to gravity tends to make the tower topple to the right. The torque due to the ground tends to make the tower move to the left. Those two torques cancel, and the tower is in static equilibrium, although it is a precarious equilibrium, and active steps have to be taken every so often to shore up the tower, or it would have long ago have fallen over. The dancer is a different story, because she's in contact with the ground at only one point, and therefore her center of gravity cannot be any place except directly above that point of contact with the ground. If that point were off to one side or the other from where her toe is contacting the ground, you can see that she would topple to the right if that force were acting at a point to the right of where I've shown it. She would topple to the left if that force were acting to the left of where I've shown it. So when there is only a single point of contact with the ground or with a pivot, then the center of gravity must be on a vertical line with that point. Otherwise, we would not have a system in static equilibrium. And let me give you an example, or prove to you now, why it is that the center of gravity and the center of mass in fact coincide. And then we'll take a closer look at our dancer. So let's go to the big screen where we do our math. And let's think about an arbitrary object, some weird arbitrary shape. Physicists love arbitrary objects like that. And let's assume it has a total mass m. And let's consider that it's made up of lots of individual little pieces of mass. And if we were calculus types, we would make them very small, and there'd become infinitely many infinitesimally small ones. But I'm just going to think of dividing this up into a bunch of smallish masses. Each of these masses experiences a force due to gravity. F1 is m1g, F2 is m2g, F3 is m3g, and there are many, 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 many more masses making up this object. I'll just think about the three of them. Now, we've already seen that any pivot point will do. If we can show that the torque is zero about any point, it's going to be zero about every point. So we're free to choose the pivot point. So I've marked a particular pivot point I'm going to think about. And we know that the torques depend not only on the forces, but on the perpendicular distances from where the force is applied to the pivot point. So there is L1, the lever arm for the force 1 acting on mass 1. There's L2, there's L3. If I want to find the torque due to all these gravitational forces on this mass, I will add up the torques due to the individual forces. L1 times force 1, plus L2 times force 2, plus L3 times force 3, and so on. Each of those is a calculation of a torque, and therefore the total torque is L1 times M1G, L2 times M2G. If you're very sharp, you notice some arrows on there. They shouldn't be there. I'm not talking about vector forces at this point. I'm just talking about their magnitudes. L1, M1G, L2, M2G, L3, M3G, and so on. Now here's the big point. If gravity is uniform, in other words, if the acceleration of gravity is the same all over this object, then mathematically G has the same value, and I can factor it out and write the expression like that. Now notice that step depends on G being the same everywhere. If I had a very large object, so big that gravity varied over it, and gravity does vary with height above Earth's surface, as we'll find, or as we found in lecture 13, therefore we we wouldn't be able to make this mathematical step. So the coincidence of the center of gravity and the center of mass is going to depend crucially on gravity being uniform, but it's approximately uniform near Earth's surface. So we can continue this calculation having factored out G. So there's our result so far. The torque due to gravity is L1 M1 plus L2 M2 plus L3 M3 ... all multiplied by G. Now let's multiply this whole expression by 1 in the form of m over m, where m is the mass of the entire object. Well, I'm going to keep one of the m's out here. I'm going to put the other m in the denominator underneath there. So what do I have here? I have the force of gravity on the whole object, the mass of the whole object times g. If I just told you I've got an object of mass m, what's the force of gravity on it? It's mg. What do I have here? I have the weighted sum of the masses, weighted by their distances from some point, namely this pivot point, their perpendicular distances from that pivot point, divided by the total mass. Well, that's exactly the expression we developed back in lecture 14 for the center of mass of an object. So this is the position of the center of mass. And so what that tells me is that the torque, the gravitational torque, the torque due to gravity on an arbitrary object, can be calculated as if the object were a single object located at its center of mass relative to the pivot point, and then we multiply that position of the center of mass relative to the pivot by the gravitational force on the entire system. So that's a proof that the center of gravity and the center of mass coincide, as I argued should be the case for my dancer and for the Tower of Pisa. That enables us to find centers of gravity or centers of mass in a rather neat way. And I'm going to do that experiment on my dancer. So here's the same dancer we were looking at in the visual a little while ago. I've got her suspended now, not on her toe, but by her hand up here on this pivot. So she's free to swing like that. And in equilibrium, as we've just discussed, she ought to swing in such a way, or she ought to end up in such a way that her center of gravity equals her center of mass, is directly beneath that pivot. If that weren't true, there would be a torque on her that would tend to swing her like that, and eventually she would come to equilibrium in that configuration. So what I'm going to do is suspend a string with a weight on it, so that string is hanging vertically, and I'm going to suspend that string from the same pivot that the dancer is hanging from. Now, I don't know yet where her center of gravity equals her center of mass is, but I do know it lies somewhere along that string. So I'm going to draw along that string once I get her to stop moving. She's actually cut out of styrofoam. And actually, by the way, I should say I'm not really finding the actual dancer center of gravity. I'm finding the center of gravity of this cutout of the dancer, and her skirt, which probably has negligible mass, is being weighted as much as the rest of her. So probably we're going to find a lower position for her center of mass than the actual physical ballerina has, because I really should take the skirt off here because it is contributing almost nothing to the mass. So it's not quite an accurate picture of where the real dancer's center of mass equals center of gravity is. But it is where the center of mass and center of gravity of this silhouette are. So let me draw a line along this string. So somewhere along that line lies the dancer's center of gravity equals her center of mass. I don't know where along the line, but somewhere. But I can find out where because two intersecting lines determine a point, and I can suspend her from somewhere else. So let me suspend her, for example, from this point, from her foot. And let me do the same thing. Now I know that her center of mass lies vertically below that pivot point. And so I'm going to hang this string, and I'm going to draw a line on which I know her center of mass lies. From that experiment, I don't know where on the line the center of mass lies, but I know it lies on both those lines, and those lines intersect at one place, so that must be her center of mass and her center of gravity. And if I want to check on that, we'll see how good our measurements were. Let's suspend her from a third point. And you can see that they just about cross, and so her center of mass equals center of gravity is right there where those lines cross. And that's a quick, simple way of locating the center of mass, that is the center of gravity, of simple structures. So there's our dancer, who in fact was suspended on that foot, and we could have done the same thing if we had been able to balance her on that foot, but that would have been harder to do for reasons I'll get to later in the lecture. Well, let's look at a more challenging way to work with a problem involving static equilibrium. This is the kind of problem that real-world engineers or other people might have to work with. So over here I have a little simple demonstration of a ladder leaning up against a wall. And I want to ask the question, how high up this ladder could I climb before the ladder begins to slip like that and falls down? I think you probably have an intuitive sense that the more steeply I prop the ladder, the safer I am in terms of it slipping out at the bottom like that. On the other hand, if I prop it too steep, it may fall over this way. So the question I'm going to ask is, at what angle can I prop it and still safely climb to some height? The further up the ladder I go, the more danger I'm in of it slipping down like that. That's a fairly sophisticated problem in static equilibrium. So let's start working that problem. So here's a person climbing up the ladder. The ladder has negligible mass, so I'm going to neglect the mass of the ladder. There's friction of the ground, but I assume the wall is frictionless. That makes the problem a little bit easier, but it's certainly not a trivial problem by any means. There is friction at the ground, and the coefficient of friction is mu. It happens to be the coefficient of static friction because I want the ladder to be at rest with respect to the ground. I don't want it to slip. And the question is, how far can you, mass m, climb? That is, what distance r can you climb up the ladder before the ladder slips? And we're going to be interested in what the angle of the ladder might be for those conditions to be met. Now, before I set the problem up in detail, let me just remind you briefly about how friction works. We looked at friction in earlier lectures. Friction is a force that acts between two surfaces in contact. It opposes their relative motion. It arises between forces between the atoms in the surfaces, as we saw, and it's proportional, and this is the important point for us here, it's proportional to the normal force between the two surfaces. So the force of friction is mu, the coefficient of friction, times that normal force, and there's a picture we saw before, and we pulled a block across the table, measured the forces, and so on. We've seen how friction works. I just wanted to remind you how friction works. So here's our problem. How far up can we climb before the ladder slips? So we're free to choose the pivot point anywhere. We've seen that. So let's choose the pivot at the bottom. That's going to simplify the math in an important way. It's not going to make the math wrong. It's just going to simplify it. I'm going to choose the pivot down here at the bottom. I'm going to first identify the forces acting on this system. What are those forces? Well, there's the force of gravity acting on the person downward. There's no force of gravity on the ladder because I'm assuming the ladder has negligible mass. Not true. We could have added that in, would have made it just a little bit more involved. There is a normal force from the ground pushing up vertically on the ladder because the ground is horizontal. Call that N1. There is a normal force from the wall pushing perpendicularly to the wall. That's the horizontal direction. I'll call that N2. And there is a frictional force, and because the ladder is trying to slip out that way at the bottom, the frictional force is going to go the other way, FF. And I think I've now identified all forces acting on that system of ladder plus person. Two forces at the bottom, friction, and a normal force up. A force due to the person on the ladder located at the point where the person's mass or weight is, and a force, normal force outward from the wall up there. Let's identify the perpendicular distances because we're going to have to calculate torques because we want there to be no torque in this situation. So let's identify those perpendicular distances, and those perpendicular distances are for this force from the pivot point for N2, it's this distance L sine theta. The whole ladder has length L. The angle here is theta. So the side opposite the ladder, which is this, the side opposite the angle, which is this distance, same as this distance, is L sine theta. The whole thing is L, the hypotenuse. The opposite side is L sine theta because sine theta is defined as the opposite side over the hypotenuse. The lever arm for the force of gravity acting is the perpendicular distance from the pivot point to the line through that force, and that's r, this distance, a hypotenuse, times the cosine of the angle, because this distance is the adjacent side to the angle. So we had a trig review before. I'm not going to bother to give you the trig review again. That is the setup for the two lever arms that determine the torques. So we're ready to go. In equilibrium, the forces and the torques both have to sum to zero. Let's look at the vertical forces. There's the gravitational force downward and the normal force at the bottom up. They've got to sum to zero so the ladder won't be accelerating in the vertical direction. In a coordinate system, vertical coordinate system, I can simply say the magnitude of the upward normal force is equal to the magnitude of the downward gravitational force. N1 equals mg. Let's look at the horizontal forces. There are two horizontal forces, the force of friction and the normal force from the wall. They've also got to balance. There's no acceleration in the horizontal direction. So the force of friction plus this normal force from the wall have to sum to zero. In a horizontal coordinate system, I can simply say the magnitudes of those two forces are equal. N2 equals mu N1, where I've written mu N1 for the frictional force because the frictional force is the coefficient of friction times the normal force acting between those two surfaces. So these two equations are the statements that the force, the net force, is zero. It's two statements because we have to worry about the forces in two different directions, vertical and horizontal, because this is a two-dimensional problem. That takes care of the forces. We've still got to worry about torques. Well, are there torques? Yes. There's a torque due to the gravitational force. It's trying to make the ladder rotate clockwise. There's a torque due to this normal force, which is trying to make the ladder rotate counterclockwise. What about these forces? That's why it was clever to pick the pivot at this location down here, because there are two forces there, but their lever arms are zero, so they contribute nothing to the torque about that point. You might say, well, you're kind of cheating, aren't you? Well, because I can choose any pivot point and it doesn't make any difference to the physics, that's okay. Those two forces still come in. They're built into these equations, but I don't have to worry about them for torques. So the only torques are a torque due to this force, and that torque is the value of the force, the strength of the force, times the appropriate lever arm, and another one for this force, the value of this force, N2, times its lever arm. And those two also have to sum to zero, or equivalently, they have to have equal magnitude because they're in opposite directions. Let's see if we've got them right. The torque due to the gravitational force is the force times the lever arm, r cos theta. So that's the gravitational force, mg, times r cosine theta. And that's got to equal N2 times its lever arm, which is L sine theta. That's a lot of math. Well, what we've got then is this. We have three equations in three unknowns. We've got the equation for force balance in the vertical direction, force balance in the horizontal direction, and that there be torque balance, that there be no net torque. All we have to do now is solve these. I'm going to solve the first one saying N1 is mg. I'm going to plug that in for N1 in the second equation. So that gives me N2 equals mu times N1, but N1 is mg, so it's mu mg. Then I'm going to take that, which is an expression for N2. I'm going to plug it in for N2 in the second equation. So I'm going to put it in there, and that's going to give me mgr times cosine of theta is mu mg, that was N2, times L sine of theta. Going a little fast here, but this is pretty simple, straightforward algebra, and now it's going to be a little bit of trigonometry. Solve that for r, the distance to which you can climb, and that's going to, m is going to cancel again. M is gone, out of the picture. As happens in cases involving gravity, that gives me that mu times L, there's the mu times L, the m's canceled. The g has also canceled. The answer to this problem is going to be the same on the moon or Mars or anywhere else, because g is canceling also. I get sine theta over cosine theta, which defines tangent of theta, and that says that mu, the coefficient of friction, times L times tangent of theta has got to be the radius to which I can climb. The bigger the coefficient of friction, the more I can higher I can climb. The longer the length of the ladder, the higher I can climb, at least relative to that length. And finally, the bigger tangent of theta, the steeper the angle, the higher I can climb. All that is intuitive. Let's work it out with some numbers. So r was mu L times the tangent of the angle theta. It turns out that the Occupational Safety and Health Administration says the minimum distance you should put a ladder base from the wall is 1/4 of the ladder length. That translates into a value for cosine theta. It says cosine theta should be less than 1/4. That makes theta less than about 75 degrees. It makes tangent of theta less than about 3.8. And if you draw that conclusion, you say you can get all the way to the top of the ladder, r equals L, safely, as long as mu tan theta is greater than 1, or mu is greater than about 0.26, if you're at OSHA's minimum angle, and you could do better by making the angle of the ladder steeper. So mu of 0.26 is a pretty low coefficient of friction, and so that's good under all but the slipperiest conditions. So it looks like OSHA has built a margin of safety into their standards here. So that was a really pretty sophisticated problem involving static equilibrium. Let me end with one other important aspect of static equilibrium, and that is the stability of the equilibria. A system may be in equilibrium, but that doesn't guarantee that the equilibrium is stable. Let me give you a couple of examples. Here's a cone-shaped object. I sit it on the table. It's clearly in equilibrium. There's no net force on it. There's no net torque on it. It's not tending to twist or fall over. I could also put it in equilibrium by balancing it very carefully on its tip, something I'm just not going to be able to do. But if I could and got it there momentarily, it would have no net force on it and no net torque on it. And yet you and I know it would be completely unstable. It wouldn't stay that way. Well, the stability of an equilibrium is related to the potential energy system, the potential energy curve for the system in question. And here's an example where we can explore that in a little more detail. Here's my car at the bottom of this roller coaster track, at the bottom of a valley in its potential energy curve. That is a point of stable equilibrium. If I disturb the car from that point, pretty soon it will come back to that equilibrium point. That's what makes the equilibrium stable. It's at a minimum in the potential energy curve. Not another stable point, but another equilibrium point. It's going to take me a little work. I can do this one, unlike the cone on its tip. There is a point of equilibrium. But it's not a stable equilibrium, because if I disturb the car slightly, it ends up going somewhere else. And eventually it will find itself in that stable equilibrium. So there are equilibria that are stable and equilibria that are unstable. An unstable equilibrium, if disturbed, is likely to end up in a stable equilibrium. It's likely to change the configuration it's in. You don't tend to find systems naturally in unstable equilibria, because pretty soon something's going to disturb them a little bit and they're going to undergo a transition to a different state. Well, is there any kind of in-between, or is that it? Yes, there is an in-between. Over here, I've got a relatively mild valley, a relatively shallow valley in the potential energy curve. And if I put the car right in that valley, it will stay there. But if I give it very much of a push up to this unstable equilibrium, then it will go over and end up in some other state. That was a point of what's called metastable equilibrium, an equilibrium that is neither fully stable nor fully unstable. It is locally stable. If the car is down in that part of the track, and I disturb it just slightly, it's going to stay in its equilibrium. But if I disturb it very much, it's going to go this way or this way and fall into another state. Actually, it fell into the lowest possible equilibrium state in this room, namely it landed on the floor. So that is a discussion of stable and unstable and then metastable equilibria. I showed you at the beginning, for example, that balanced rock. It is in stable equilibrium, but it's not very stable. You push it a little bit. Don't have to give it much energy to get it out of that stable equilibrium, and it will topple over into a more stable equilibrium lying on its side. So there is a relativeness to the stability of equilibria. This deep valley is the most stable equilibrium on this track. There's an even more stable equilibrium that my car ended up with on the floor. Here's another valley. It's not quite as deep as this one, and so it's a little bit less stable because it's a little bit of a higher energy state. And this idea of stable and unstable equilibria, although I've described it for my simple roller coaster track, holds for all kinds of systems, from semiconductor devices that we engineer to electrons in atoms, all kinds of systems. These considerations of stability and instability apply. Things get more complex when we're in multiple dimensions. Here's a picture of a saddle-shaped surface. The equilibrium here at the saddle point is stable in one direction, but in these two dimensions, it's unstable in the other direction. So things get more complicated in multiple dimensions. Well, let me end with a quick summary of what we've done here with static equilibrium. What's required for static equilibrium is both zero net force and zero net torque. What's required for stable equilibrium is that a system must not only be in equilibrium, zero net force and zero net torque, but it must be at a minimum in its potential energy curve. And it's at those stable equilibrium points that we therefore tend to find systems in both nature and engineered systems.